Good morning. This is just a quick video about the gravitation homework, classwork, castle learning stuff. You started it yesterday. So if you need all the solutions, here they are. So the first one, what is the magnitude of the gravitational force of attraction between two 0.425 kilogram soccer balls when the distance between their centers is half a meter? So the new equation from yesterday, and we're going to substitute into that. So for the sake of space, I'm not going to use units. 6.67 times 10 to the negative 11 times the mass, 0.425, and the same mass because there's two of them. It's all in the numerator. Divided by the distance between them squared. So, as I said yesterday, a lot of this chapter is just going to be plugging everything into your calculator correctly. Let's see if I can do that. Is that one of the choices? 4.8, yep, so it's choice 2. I like this question. It says, what happens to the force of gravity as... Oh, never mind. But essentially, what happens as you increase your force of gravity? What's going to happen to your distance as you increase that as well? Are you going to get a larger or a greater force? So everything in the numerator stays the same. So as I increase my radius, I'm going to be dividing by a bigger number, and it's also squared. So if I double my radius, I get 4 times. If I or 4 times less because I'm dividing by 4. If I triple it, I get 9 times less. If I quadruple it, I get 16 times less. So what's going to happen is as we increase our radius, we are going to decrease our force. So choice 1 is out, choice 2 is out because they show it increasing trend. So it has to be 3 or 4. And the answer is choice 4 because as we increase the radius here, we'll keep dividing, but we'll never actually get to 0. And this one shows that we'll have Fg equals 0 at some point. This curve shows that we'll get close, but we'll never quite get there. Question 3, I love this one. It's going to be on your test, and everyone's going to miss it. But hold on, let me just show where this was a little bit easier to see online. Had the planet or the sun and satellite and Earth are separated. So the gravitational force of attraction is a force of attraction. So everything with mass is attracted to each other. So this has to be choice 3. The satellite is pulled towards the Earth, and the Earth is pulled towards the satellite. You could also just think of Newton's third law. Every action has an equal and opposite reaction. So if the satellite pulls the Earth pulls the satellite. Now, which one has more acceleration? F net equals ma. So if you have the same force but you have less mass, you're going to have more acceleration. That's why the satellites will do the orbiting and the big planets will kind of stay in the middle. This question down here, when the Earth and Moon are separated by that distance, they have a force of 2 times 10 to the 20th newtons. What would be the magnitude of the gravitational force of attraction if the Earth and the Moon were separated by this distance? So let's see. You could either solve this out, or we could see 3.84 divided by 1.92. Alright, so we're at half the distance. So we could plug all the numbers into this equation and solve, or we could say, alright, we have half the distance we had before. And what happens? What do we have on this side? Well, 1/2 squared is 1/4. So Fg divided by 1/4 is the same as 4 times Fg. So we have 4 times our original force. So 4 times 2 times 10 to the 20th is going to be choice 4, 8. As you bring things closer, it should increase. So you should have been able to at least rule out choice 1 and 2 because they're closer to each other. But yeah, it's going to be 8 times because r is squared. Question 5, I think, is the same as question 2. And again, it's going to be choice 2. And that's because we have fg equals big G m1 m2 divided by r squared. And this is really, you could think of it as the same as the y equals 1 over x squared type of curve, in case that helps you in your thinking. Alright, we have 2 satellites, equal mass, A and B. One's at radius r, the other's at r, or 2r. Compared to the magnitude of the gravitational force between satellite A and the planet, the magnitude of the gravitational force of B. So here we have Fg equals big G m1 m2 over r squared. So that's our radius, or we could call it capital R if we really want to. And now we're at 2r. So we've doubled our radius. So if we're essentially adding a 2 squared to the bottom over here. So since we added a 2 squared on the right, we need to add a 2 squared on the left. 2 squared is 4. So we have 1/4 as great. Problem 6 is the opposite of problem 4. Problem 6, we got twice as far away, so we have 1/4 fourth. Problem 4, we got twice as close, so we had 1/4. Not 1/4, but 4 times. Question 7, I'm going to write out over here. Oops. Let's go. So you had choice 1, because we're going to do the same thing, m1, m2 over r squared. Choice 2, m1, m2 over r squared. 3, and, oh, did it get a little blurry? I'm just writing some stuff out, so we can solve this in a moment. Come on. There we go, we're back. So they're saying the gravitational force of attraction between two objects would be increased by, so I have choice 1, 2, 3, 4. This is all for question 7. This one says doubling the mass of both objects. So if I double m1 and double m2, I added a 2 times 2 to the numerator, so I get 4 times the force. That looks good. We increased. The choice 2, it says doubling the distance between the objects. So if I double this, I added a 2 squared to the bottom, so I'm dividing by 4. That's less force. That does not look good. Choice 3 says doubling the mass of both objects and doubling the distance. So I double the m1, double m2, and I double the distance. So 2 times 2 on the top gives me 4. 2 squared on the bottom gives me 4. They actually cancel out, so I didn't actually change anything. 4 on the top, 4 on the bottom. And the last one, doubling the mass of one object and doubling the distance. So I added a 2 to the top, and I added a 2 squared to the bottom, which is a 4, so this is actually decreasing it as well. That doesn't work. So it is choice 1. Again, that's what I got, but I just wanted to check the other 3. Question 8. What is the magnitude of the gravitational force between an electron and a proton that are separated by a distance? Oh, tricky. So we're going to need our reference table here. So we have Fg equals G m1 m2 over r squared. So we get 6.67 times 10 to the negative 11. And now I need the mass of an electron, which should be on my reference table. Mass of an electron is 9.11 times 10 to the negative 31 times the mass of a proton, which is on my reference table. 1.67 times 10 to the negative 27. And they are separated by a distance of 1 times 10 to the negative 10. But remember, we got to square that whole value in the denominator. So I get my calculator, and make sure you watch my keys. So you get 6.67. Then you want to hit second and get the E key to pop up. because you don't need any parentheses now, and then you hit negative 11 times 9.11 e times 10, or negative 31 times 1.67 e negative 27 divided by 1 e negative 10 squared. Hit enter, and we got 1 times 10 to the negative 47. Choice 1. Alright, last two questions. Alright, this is the same equation. We have 6.67 times 10 to the negative 11 times 7 kilograms times 7 kilograms, a distance of 2 meters squared. Calculator, 6.67 e negative 11 times 7 times 7 times 2 squared. Oh, not times 2. Divided by 2 squared. Enter. Okay, 8.17 times 10 to the negative 10. So looking here, you should know it's either 1 or 3 because it's the same value. So chances are, if you just had to guess, you should guess one of those two. Bettering your chances. And now this one's a big long question. Basically, it explains how the planets pull on each other. Even though they're all the planets are orbiting, not drawn to scale, please. Orbiting the sun, but their orbits aren't perfect circles. And then part of that reason is because the planets also pull on each other. Okay? So they pull. But the amount of force that the sun pulls on the planets is greater, and that's why for the most part they're orbiting just the sun and not orbiting one another. So there's a little kind of wiggle wobble to them from the other planets pulling, but most of the gravitational force is from the sun. And this is actually how we found Neptune. They calculated that it should be there. They took their satellite and they pointed it and they saw it, and they were like, whoa, we found it. So basically it's saying if Neptune's closer, why does the sun still effective if the sun's so much further away? And that's because the distance is not the only variable that is in the equation. Mass is also here. So because the sun has such a great mass, it doesn't matter that Neptune's much closer. Sorry, just got a notification. The mass will triumph. But that's it. Those are the 10 questions. Hopefully that video helps.